on this computer. That's good. And then share the screen. That's okay. I hope everyone can see the screen. If not, I'll get an orange flag coming at me. So we're going to do confidence intervals for the next 2 or 3 lectures. The first one, I'll look at it as sort of a more elementary way, and then we'll see how we can sort of abstract that a little bit. And then I'm going to look at a second or a third way to abstract the building of confidence intervals in the next lecture. And then we'll look at Bayesian approaches where it's not called a confidence interval anymore. It's called what's it called? It's called I'll think of it. So credible interval. So I'll give you an overview. I'll look at Z intervals and T intervals, and then I'm going to look at this correspondence between two-sided tests and confidence intervals. That will give me sort of a general procedure that we can talk about, and then I'll use that, and I'll talk about the interpretation of a confidence interval so you can tell your friends. So if I told you, here's my estimator, here's its bias, here's its variance, you sort of need all you need to know. If you're good at probability and statistics, you can compute essentially any quantity you care about. But typically, the way we present estimation is to use something about where the parameter has a high probability of being. So for interval estimation, given data X, we replace the points estimator for the parameter by a subset of the parameter space. Now I said interval estimation, but this could be a higher dimensional situation than one. If you had, for example, 2 independent normal random variables, then you can imagine creating a circle. I guess if they're independent and have the same variance, you would create a circle, and that circle you could enlarge off of the center until it contained 95% of the variance. If the standard deviations were different between each of the 2 random variables, that circle would become an ellipse. And if there's a correlation, that ellipse would not be parallel to the axis, but lift off the axis to reflect the correlation between the 2. So we'll consider both the classical and Bayesian approaches. Okay. So some definitions that we have to learn. So if I give you just any subset of the parameter space, and then you plug in your observations, you'll get a random subset of the parameter space, and I can ask the question, if theta is the true state of nature, what's the probability that parameter lies in this random set that I just picked? And that has a name, it's called the coverage probability. Okay, you typically want to be thoughtful in the way you pick this random set C of X. You want to pick it that it has high probability. I'll use the letter gamma for containing the true parameter value theta naught. And you may want to do better than that. You don't want to have, since we typically don't know the parameter, you want to pick that random set in such a way that no matter what parameter value you have, the probability, if that is the true state of nature, that your parameter lies in this random set is at least gamma. And if that's the case, we call this set C hat of X a gamma level confidence set. So for a single parameter, you're used to the simple choice of an interval. The interval could be two-sided. There's an errant comma in there. It could be, so I'm going to call the lower, so that means there are 2 estimates. There are 2 statistics. One is theta L hat, and the other is theta U hat. It depends just on the data. It doesn't depend upon the parameter, so it is a statistic. And so your confidence set is just the set of thetas that are between your lower estimate and your upper estimate. And we could write that just as a random interval, and you'll see that in a minute. Sort of theta hat L given the data X, theta hat U given the data X as your closed interval. Often what you'll see is an estimate for the parameter, the usual point estimate that we've seen in the past and then you'll take from that and subtract a quantity m of x for your lower estimate, and you add a quantity m of x for your upper estimate. And the m is typically called the margin of error. And sometimes you'll see that more succinctly written as theta hat x plus or minus m of x, where m is the margin of error. So for one-sided confidence intervals, you could pick parameter values less than some theta hat u of x, and you could write that interval as from minus infinity up to theta of u, or whatever the minimum of your parameter space happens to be. And then you could also have an upper confidence bound, or the random set C of x is the set of thetas that are above that are above theta u of x. It should be a theta L of x. I'll fix that. There, it's fixed there. The interval from theta L of x to infinity, and that's called the lower confidence bound. We'll see in a minute that R does that for us. But in fact, maybe I'll show it to you quickly. But well, I'll wait to show it. But it's not so unusual that that's the case. So Walter Pigor studies risks and toxicity, say for a drug. Let's pick a random drug that is often used for malaria that might help with COVID with very scant evidence. And so you might want to worry about its toxicity. You're typically not worried about the highest toxic level where you have a good chance of being safe. You're only worried at the lowest level where you might fail to have be safe from toxicity. So in those cases, we're only looked at a lower confidence bound. So sometimes only the lower end really matters for the questions that you have. If you're making an estimate, and I have a friend who's sort of presenting things to Immigration and Naturalization Services. If you're making an estimate of the situation of people, then all you really need to say is give a lower bound for the fraction, let's say people who are coming here to the US. You need only a lower bound for the nature of what happens to them, saying that I have a certain confidence level that it's at least that bad. It does in that case, yes. So when we use the margin of error, those are for symmetric confidence intervals. We will get away from that as we go on. But the typical thing you see in the newspaper, I saw it today in the newspaper, are those cases where you have an interval that's symmetric around the point estimate. Okay, so if I have normal random variables and I don't know the mean, but I do know the variance, then I can write down a standard normal from that, x bar minus mu over sigma naught over the square root of n, and pick an alpha between 0 and 1. So we've seen this notation before. We'll let z alpha satisfy the probability that my standard normal is above that has probability alpha. So you'll see some alpha over 2. It's just like you see in two-sided tests, and we'll talk about the relationship between two-sided tests and confidence intervals pretty soon. So there it is. I just drew a little picture for you. So there's the z alpha, and above that level z alpha is probability alpha. That's the area under the curve to the right of that vertical red line and above the x-axis. So equivalently less than that, right, because probability is add to 1 is z less than or equal to z alpha is 1 minus alpha. So that's called the upper tail probability with critical value z alpha. And so if you go back to the old days, you will often see tables, and the tables will list those upper tail probabilities for different values of alpha. But now we just compute it with R. So if you want 2.5% above, you just write Q norm of 0.975. Let's see, and you get, might as well do it. I wonder why. Okay, so you get QNOR. They're almost 1.96. Okay, so to get a z interval, we'll let gamma be 1 minus 2 alpha. You'll see why in a minute. So alpha is 1 minus gamma over 2. So for example, if gamma is 0.9, then alpha is 0.05. If gamma is 0.95, then alpha is 0.025, and so on. If gamma is 0.98, then alpha is 0.01. I'll let you do the algebra. And so you do that so that the probability that you're between minus z alpha and plus z alpha is gamma. And so if I can plug in for z the quantity that I care about, then and that z is a standard normal, then I get out of that a gamma level confidence interval. So we'll do that. So I'll let mu naught be the state of nature, and I'll isolate mu naught in each of these two quantities. So on the one hand, x bar minus mu naught over sigma naught divided by the square root of n is the z, and I want it to be less than z alpha. On the other hand, I want that same quantity to be at least as big as z alpha. So I'm going to isolate mu naught in both equations. So I'll multiply through by sigma naught over the square root of n. On the equation on the left, I'll do the same thing to the equation on the right. I will subtract z alpha sigma naught over the square root of n on the left-hand equation and move mu naught to the other side of the equation for the left column. And for the right column, I'll move the, I guess what I do is I move the z alpha over, I get a plus sign, and then I multiply through by -1 to flip the sign. So I get mu naught is less than x bar plus z alpha sigma naught over the square root of n. And I did that little funny bit of algebra so that the mu naughts were put together in the end so I can create one inequality. X bar minus z alpha sigma naught over the square root of n is less than mu naught is less than x bar plus z alpha sigma naught over the square root of n. It has probability gamma. So this has the symmetric property for a confidence interval, right? The estimate, I estimate for mean, in the mean is x bar, and then my margin of error is not random, right? It's z alpha sigma naught over the square root of n. So you could write it this way: for data x, that is my x bar plus or minus, right, because it's a symmetric confidence interval, z of 1 minus gamma over 2 sigma naught divided by the square root of n. So that's a two-sided confidence interval with confidence level gamma, right? X bar is the estimate for mu, and z 1 minus gamma over 2 sigma naught over the square root of n is the margin of error. Okay, so if I want a 98% confidence interval, let's see if I can, I have my sheet of paper here so I don't have to remember. Maybe I do.
What happened?
Yeah. Is there a question? So let me write it down on my sheet of paper so I don't have to keep referring to it. So 98 is my confidence level, sigma naught is 2, n is 25, and x bar is 3.71. So I can use that to build the confidence interval. So I'm going to call the amount that I add z star, and that's q norm, since I'm after a 98% confidence interval of 99. And there's a question. I thought there was a question. There it is. Oh, okay. You're forgiven. Let's see. So, okay, and then sigma naught was 2. N is 25. Whoops. And okay, that's all I really, and then sigma naught. And then I can get the margin of error by, let me just sort of display it, is z star times sigma naught divided by square root of n. So there's the margin of error, 0.98. And so if I look at if x bar is 3.71, then the lower limit is that, and the upper limit is that. So that's, whoops, is, now I probably ruined myself here by putting equals. So let's go back there, and then plus. There's the upper limit. So that's just how you build a confidence interval quickly. Go back to the slides. Okay, if you have unknown variance, then we replace the variance sigma squared with its unbiased estimator, and that statistic is known as t. We've seen that before. So there it is. And then, so S over the square root of n, which estimates the standard deviation, you'll see the word standard error that replaces standard deviation for estimates of the standard deviation of the statistic, or the sample. It's called the sampling distribution, I guess is the right word to use. So S squared is the unbiased sample variance, and we know that the distribution of x bar minus mu divided by S over the square root of n is known exactly and depends on n, the number of observations. It has the t distribution. And the number of degrees of freedom that go with that t distribution is n minus 1. So we're in good shape for this. So the confidence interval is again symmetric. You could go through the same process. It'll just be x bar plus or minus, and then rather than having a z, you'll have a t, and the t needs two subscripts, one for the number of degrees of freedom, n minus 1, and then one for the confidence level, gamma, so it's 1 minus gamma over 2 times S over the square root of n. So I've drawn for you the density of a standard normal in black, and the density in brown of a normal random variable. I'm sorry, a t distribution with 4 degrees of freedom, or t density. And then I did the same thing with the distribution function for the standard normal, and that's black, and then it's almost brown. T is brown is the random variable, again with 4 degrees of freedom. So there's additional uncertainty that arises from the need to estimate the standard deviation in the t distribution. So if you look at those two plots, you can see in the top that the tails of the brown distribution, the t distribution, are fatter than the tails of the black or normal distribution. So that means that more of the probability is going to be further out, and so you can expect the critical values to get bigger as you go further out. For the bottom distribution, you can see that the normal distribution sits under the graph of the normal distribution function sits under the graph of the t distribution function for values below 0, and it sits above the t distribution for values greater than 0. So that's another way of saying that the distribution is more spread out, and so then the value for the t distribution is going to be bigger than the value for the z distribution in order to have, say, 5%, 2.5% below and 2.5% above, and so it's going to give you wider confidence intervals. Although those confidence intervals get closer and closer to the z distribution as you increase the number of degrees of freedom. So I create a little table here just by writing down the critical values for degrees of freedom. I can't remember where I started, a very small number, 1 or 2. And then I went up to 50, and by that time the difference between the z distribution and the t distribution is negligible. We learned last semester that the t distribution converges to the standard normal as the number of degrees of freedom goes to infinity, and so this is just a fact about that. That means that the probability that it's below a certain amount will converge as long as the distribution is continuous, but the distribution for the normal is always continuous, so we're fine. The other thing I want to point out, so I did the 95% interval and it's bigger, and so the larger you make the confidence level, the higher the probability that you want to have that captures the parameter, in this case the mean. And so if you want to have a higher probability of capturing that value, you need a wider interval. One way I think about it is if you had a basketball hoop and you could shoot free throws that went through the hoop with probability 0.9, then there's 2 ways to improve your chance of getting it through the hoop to make it probability 0.95. You can practice, or you can make the hoop bigger. And so making the hoop bigger just gives you that blue line. And then you can see 98 moves up some again and 99 again. So the larger you make your confidence level, the wider you have to make your interval. Okay, here's a classical data set which sort of interested me, so I'll do this. So Michelson tried to do measurements on the speed of light. So that's a long story, how we got to the speed of light. Galileo did it some centuries before that. What he did was he had 2 people stand on mountains that were some distance apart, and they shine a lantern, and then he had one guy reveal the light in the lantern, and as soon as the other guy saw it, he would move his cover for the lantern, and then the experimenter would mark the difference between those two events, and they got out of that the speed of light was really fast. But that's sort of all they could do. That really wasn't a high quality experiment. Morley did another experiment to get the speed of light. He did 5 actually that consisted of 20 consecutive runs. And this is the original data. And I coded it in kilometers per second. And I left off the last 3 digits. So it's 299 and then the 3 more digits, so I don't have to carry them with me. So this data, this Morley data, is actually stored in R, and you just do Morley $speed, and you get, for the mean, 852, and for the standard deviation, 79. And I wanted to do a t interval. Okay, there's 100 measurements, right? There are 5 experiments, each consisting of 22 consecutive runs. So the number of degrees of freedom is 100 minus 1, so that's 99. So the critical value for t is 1.98. So on these, the 95% confidence interval is 299,852, right? That's the mean, plus or minus the 1.9842 is the critical value, or this for the t statistic. So, and then the 79 was the standard deviation divided by the square root of the number of observations. So it's 299,852.4 plus or minus 15.7. So it's very accurate. That's the good news. The bad news is it doesn't include what we consider to be today's speed of light, which we consider to be 299,792 kilometers per second. So Morley's experiment was pretty precise, but it was a little high. I don't know why. I haven't heard any. I've tried to figure out why they missed it, but it was fun to see that this classical experiment didn't get the confidence interval, and it's not particularly close, right? Because if my margin of error is 15.7, then that's my estimate for the standard deviation of the mean, and you can see that it is 30, 40 kilometers per second below that, and so it's off by 3 or 4 more standard deviations. I'll let you, well, in order to do the 90 and 98% confidence interval, then you would just replace this QT. I won't do all of it, but you would just replace this QT. For 90, you would just 0.9599. You would use that value, and then for 95, you would use 975. You use the value 1. Oh, that's the one I did, so I forget which one I asked for. Maybe it was 98. So then you would plug in those values, and it would get you a wider confidence interval in the case of the 90% confidence interval, and a smaller one in the case of a 95% confidence interval. The 99% one is not going to get you, not going to still capture the true mean. That's the way it goes. So it was a great experiment. You got the first significant digits right, but its estimate was off. Okay, so the confidence interval is typically determined by finding the variance of the point estimator using normal approximation. So we use the t distribution all the time, even if we don't know that that my data are normal. And so we use a normal approximation as given by the central limit theorem. And when we did the t-test, I gave you sort of rules of thumb about when you can use the normal approximation, and you can do the same thing here. So in case where the variance is unknown, the distribution variance is replaced by the variance estimated from the observations. And then there's a word that you want to use. So typically this x bar minus mu divided by sigma of the square root of n is called a standardized score. And in honor of Gossett, who created the t-test under the name student, we call this standardization of the data, where we have to estimate the standard deviation as the studentized score. So then a gamma level confidence interval has the form some estimate plus or minus some critical value for the t statistic times the standard error. And that standard error is the 1 minus gamma over 2 critical value, and you have to pick the number of degrees of freedom. We'll see in this particular case that it's almost always n minus 1. We'll get other values for the number of degrees of freedom. We'll do a 2-sample example today, I think. We'll see how that goes, see what I put in there. And then later on, we're going to do other sort of test. For example, if you want to test for a confidence interval for a slope of a line, then the number of degrees of freedom turns out to be 2 fewer than the number of observations. Okay, so you may have noticed that there's a correspondence between the two-sided test and confidence intervals, and then the next part of the lecture is going to exploit that fact. So there's the picture. So I have mu naught in the middle of that picture, and it is the true state of nature, which I don't know. Then I have the sampling distribution that comes out of that, if that were the true state of nature. So that's that blue curve. You could think of it either bell curve for the normal or another curve that's for the t-distribution. And then if mu naught is my hypothesized mean, then I have critical regions, and for a two-sided test, those critical regions require two vertical lines, and there they are. One on the left and one on the right, they're red dotted lines. And if I want an alpha level confidence interval, then I have to arrange those vertical lines at the place where the area above and below them is alpha over 2. I guess since I wrote that the width is s over the square root of n, then I'm thinking about the t-distribution. Okay, so that's the curve. Now, I'm going to look at two values of x bar. If x bar is in the critical region, like it is for the red one, then the margin of error for this confidence interval is exactly the length that it is from the center line at mu naught over to the dotted line. So if x bar is in the critical region, that horizontal bar that's centered at x bar does not make it to include the mean mu naught. And on the other hand, if x bar is close to mu naught, then I create an interval that has the same area above and below that's equal to the margin of error. And so if x bar is in the region where I failed to reject, then my confidence interval does include the probability. So we have this correspondence is we fail to reject with significance alpha. That means that the t-statistic is small. If the t-statistic is small, then I'm just going to do a little bit of algebra on that, or I'll multiply through by, I didn't do anything. I just say what absolute value of small meant. And I wrote it a little oddly. I put mu naught minus x bar, and that's just to make the algebra easier in just a minute. So then I clear the denominator by multiplying through by s over the square root of n. And then I'm going to move the x bars over. And so failing to reject is exactly the same as mu naught being in the confidence interval. So mu naught is in the gamma equals 1 minus alpha confidence interval. So there's this relationship between confidence intervals and significance level as long as gamma and alpha add up to 1. Okay. So you probably saw all this in an elementary or your freshman or sophomore level statistics class, maybe not explained so mathematically. So what I want to do this in a more general setting. So here's a theorem. So I'll let theta naught be some parameter, and I'm thinking about a real parameter, a parameter space that's a subset of the real line for this. And I'll let A of theta naught be the acceptance region of an alpha level test for this two-sided hypothesis. Theta is theta naught or not. Theta is not equal to theta naught for the alternative. And so I'll let X be the data, which comes from the sample space. And what I'm going to do is I'm going to find C of X to be those parameter values so that X is in the acceptance region. Okay, so almost by definition, C of X is a gamma equals 1 minus alpha confidence set, or at least its coverage coverage has probability gamma, right? Because the probability given theta naught, or given any theta naught that I'm in this region it's the acceptance region for an alpha level test. And so you accept it with probability 1 minus alpha. And so the probability you're in there is gamma equals 1 minus alpha. Okay. Conversely, if C of X is a gamma confidence set, then for any theta in the parameter space, I can define A of theta naught be the data which have theta naught in that possible confidence set. And so then A of theta naught will be in the acceptance region of an alpha equals to 1 minus gamma test. And so here's the proof. So the proof of that is, so I have two things, maybe we should back up. I'm making two claims that if I define C of X to be this thing with respect to the acceptance set, then I get a 1 minus alpha confidence set. On the other hand, if I take this C of X as a 1 minus alpha confidence set and I define this acceptance set, then I get it, that is the acceptance region for an alpha level test. Okay. So the proof is theta naught is in my confidence level if and only if X is in my acceptance level. So you can just check that out, right? It's written sort of up there, right up there. If theta naught is in C of X, that's true if and only if, almost by definition, A is in the acceptance level set. So they're the same set. So if I plug in data, capital X, then they have to have the same probabilities. And so we'll call that common probability gamma. Why not? So then C of X is a gamma level confidence set by that information on the left. And in addition, the probability that theta naught is not in that confidence set is the probability that X is not in the acceptance region, which means that X is in the rejection region. And we know since the probability of it being in the set is gamma, the probability of not being in the set is 1 minus gamma, and that is alpha. And so A of theta naught complement is the critical region for an alpha level test. So sort of easier to understand than it is to say. Okay, so you can do this for one-sided tests and one-sided intervals. So in terms of a one-sided test of means, so let's say my alternative is greater than mu naught. Then if I pick observations that are normal, but I don't know the mean and I don't know the standard deviation, then the test statistic is going to be this t statistic, x bar minus mu naught over s divided by the square root of n. And for an alpha level test, I accept if t is not too big. So that's the set of data so that the t statistic is below t alpha n minus 1. That is, it's got a upper tail probability of alpha, and there's n minus 1 degrees of freedom. So I put in what t is, and I isolate x bar just like I did before, and that says that I will accept if x bar is below mu naught plus t alpha minus t with the critical value for an upper level tail probability of alpha with n minus degrees of freedom times the standard deviation over the square root of n. So the one-sided confidence interval is just, I'm going to now isolate the x bar, isolate the mu naught. It is just x bar minus, did I do that right? X bar minus t alpha, oh, that should be to infinity. So it should be x bar minus t sub alpha n minus 1 s over the square root of n up to infinity. Because its mu is greater than that. Okay. So, and let me show you how that works in R so you can see it. Whoops. Oh, I won't use what I had yesterday. So if I do t-test, and I'm just going to put in 24 normal random variables. I'll put in mu as 0. Actually, it doesn't matter what I put. Well, I'll put in mu as 0. I'll do that anyway. I'll put mu as 0 because that's what the true mean is. And then I'll put alternative equals greater than. Oh, I have to say greater. Oh, I said mu is 2. Okay, so So it's going to reject mu is equal to 2, but it gives the 95% confidence interval between negative 0.05 up to infinity. And the mean was 2.85, but that's too bad. If I pick, if I pick 0 as the confidence interval, let me do this. Let me fix my data so I can apply the test twice. So x. Okay, now if I do the test with x, then again it rejects it. It really rejects it, and it gives me a lower level t-statistic, or a level of confidence of 0.33. Now, if I change the mu to 0, it just doesn't care. It may accept it, but it doesn't really impact the confidence interval at all. So that was the point of my little commentary, that if you just want a confidence interval, it doesn't even matter what you pick for the null hypothesis mean value. All that matters is you pick the right alternative. Okay, let's see. So for two sample t intervals, we actually have two choices. So that means mu1, mu2, and variance is sigma 1 squared and sigma 2 squared. In the matched pair cases, these measurements are the same individual, so n1 and n2 are necessarily the same. The example that I gave you in the homework is n was a number of years, I think about 11, and I looked at monsoon rains for those in July and August for those 2 years. So those are paired measurements. And so what you do in that case is you look at the difference in those measurements, mu1 minus mu2, and so you want to, in this example, a 95% or confidence interval for the difference in rainfall between July and August. Is it rainier in July or rainier in August during the monsoons in Tucson? There's the variance, and you would just compute the variance of the differences, right? You can subtract them one by one for each year, and compute the variance. And so the variance of x bar, the averages will be just the variance you get by subtracting them and computing the variance and dividing by n. So we actually have to use sample means there. So S is the standard deviation of the differences in the paired observations. Then the gamma confidence interval for mu1 minus mu2 is the estimate for the mean difference, which is x1 bar minus x2 bar, plus or minus the t distribution with n minus 1 degrees of freedom, and upper tail value 1 minus gamma over 2, and then times S over the square root of n. So that's what it looks like for matched pairs, and it has n minus 1 degrees of freedom. If you wanted it for independent samples, then we've seen the test statistic that I've written here. T of x is the difference in the sample means x1 bar minus x2 bar, but then you use the estimate of the standard error for that difference. And so it's going to be, the variance will be S1 squared over N1 that comes from X1, and S2 squared divided by N2 that comes from X2. And then the variance of the difference is the sum of the variances. So that's why you have S1 squared over N1 plus S2 squared over N2 added, and then you take the square root. So that's the t statistic. And so if you want to do an acceptance region for a one-sided test, then you would let, you would look for the, oh no, for a two-sided test, excuse me, you would let the, you would pick the absolute value of the t statistic, and you would want it to be big, and then the number of degrees of freedom you have to compute in a particular way, and that should be alpha over 2. And so you can turn that into a confidence interval. And so the confidence interval is going to be x1 bar minus x2 bar plus or minus the t distribution with new degrees of freedom times that value 1 minus gamma over 2 times the estimate of the standard error, which is just comes straight from the denominator of the t statistic. Now recall that that statistic does not have exactly the t distribution, but Welch and Satterthwaite provided an approximation to the t distribution, and they out of that gave you an effective number of degrees of freedom, which had a complicated formula. And so that's what we typically use. So if I go back to my malaria data, then we have this transgenic line of mosquitoes that was developed to interfere with the ability of mosquitoes to metabolize a blood meal. And we used R to create a 95% confidence interval for the difference in mean lifetimes between the transgenic and wild-type mosquitoes. So all I have to do in that case is write t-test wild-type transgenic. It automatically assumes the mean difference is 95%, and it automatically assumes that what I want is a 95% confidence interval. And so there it is, the Welch-Satherthwaite computation for the number of degrees of freedom is around 170. The t-statistic is 2.4. So you know that the p-value is pretty low. I wiped out the part of the display that gives you the p-value because I'm focused on the confidence interval. So the 95% confidence interval goes from, this is a measurement of the life of these 88 wild type and 99 transgenic mosquitoes. So the 95% confidence level is that the wild type lived between 3/4 of a day and 7.7 days more, or wild type, than the transgenic. So it does shorten their life by that amount, somewhere between 1 and 8 days. If you wanted to know better than that, then you would just have to collect more data. So if I want to use the output, I'll use the output to recreate that 95% confidence interval. So let's see, the standard deviation was 12.99 for the wild type data and 10.78 for the transgenic data, and they're 88 wild type and there are 99 transgenic. Okay, so let's do all that just so we get used to seeing how it works. So I need to keep track of the means. So the mean of the transgenic is, or the mean of the wild type is 20.784, and the mean of the wild type is 16.545. Okay, so I'm going to have some round off errors. I may not get exactly the same. So, whoops, I want to go back to R. So I need, an S1, which was 12.99, and an S2, which was 10.78. You can correct me if I'm wrong. And then need an N1, which was 88. And an N2, which was 99. And I need an X1 bar, which is 20.784, 20.784. And I need a X2 bar, which is 16.545. I'll do all that. And then I want a T star, and that's going to be the critical value for the T distribution. I want 95% and 169.6 degrees of freedom, more or less. I can't remember exactly, but there it is. Okay, so then the margin of error is going to be a T star. Let's put parentheses around it. T star times the square root of S1 squared divided by N1 plus S2 squared divided by N2. Let's hope for the best. So 3.5, and then I'll look at the mean diff. I'll call it diff bar. Is at X1 bar minus X2 bar. So 4 days. So it looks like I may get it. So diff bar plus M is 7.7 and minus M is 0.076. Okay, so if I wanted to change to a 98% confidence interval, all I would have to do is replace T star with QT. If I wanted a 90% confidence interval, let's say I'd go 0.95, and then everything else would stay the same. Oh, I forgot the degrees of freedom. Where is it? 169.6. So it's 2.9. So I picked a smaller confidence level, so the margin of error decreased. And if I look at the confidence interval, it's narrower. It goes from 1.33 days to 7.14 days. So if you're happy with lower confidence, you can get a narrower confidence interval. Okay. So now I'm going to talk for a few minutes about the interpretation of a confidence interval. If you want to have fun, look for a newspaper article that has a confidence interval and watch them try to interpret it. So a confidence interval with parameters based upon two statistics, right? The lower end of the confidence interval and the upper end of the confidence interval. As with all statistics, you're not allowed to use the value of the parameter in order to build the statistic. That's what statistics are. So that means that before I even show you the data, you're going to write down the formula in advance of seeing it. So the way I like to think about it is the term confidence can be related to the production of that confidence interval. So I told you how to produce it, right? For an arbitrary amount of the data, I build these two values, theta hat L and theta hat U, and then when the data come in, I get a confidence interval. So the term confidence is related to the production of the confidence interval. So if we produce independent confidence intervals repeatedly, then each time we may either succeed or fail to include the true parameter in the interval. And so you can think about that as a Bernoulli trial, and the Bernoulli trial has success probability gamma, or at least gamma, I guess, if we're trying to be conservative. So that's the way to think about it. You often hear that 95% confidence interval means it contains 95% of the data. If you think about it for a minute, that's sort of crazy, because if you get more and more data, the confidence interval gets narrower and narrower until it could include very little of the data, but particularly if the standard deviations are really big. So then I just, for fun, yesterday built 100 confidence intervals from simulating normal random variables and constructing the intervals. And then I asked myself which ones failed to include 0. So if I scan across, I see one that's too low at, around 30. I should have put vertical bars at multiples of 20, but around 37. Another one that's too low at around 44. They're all too low, the ones I picked, at 59 and 61. And then there's another one that's probably too low, around 90. So that's 1, 2, 3, 4, 5 that did it. None of them were too high, oddly. So so if you do 100 confidence intervals, on average, you're going to have 5 that fail to include the so I'm going to do, I'll do 20, I guess, out of 100 with probably 0.05. So, but it can vary around that. So here's me just looking at 100 examples of confidence intervals. I'll do 20 random samples of confidence intervals, of 100 confidence intervals, and this will tell me how many fail to work. And you can see it's around 5 a lot. Sometimes you get really lucky and it's only 1 or 2, and sometimes you get really unlucky. It's up to a 10 or 11. So Nate Silver talks about this all the time. that, and he's caught a lot of pollsters doing these things, that if you really do independent polls, then 5% of the time your poll should not contain the confidence interval. If it contains the confidence interval every time, then there's something wrong with what you're doing. And he has caught a couple of pollsters doing that by essentially cheating, looking at other polls before they make their announcement. So, so that's one thing that you can also look at in terms of the honesty of confidence intervals. It reminded me of a funny situation that I had a few years ago when the lottery got very, very big. Nobody won it for quite a while. And so they asked me, for the purposes of the radio, to tell me how many people that I would think would win. And so, so 538 guessed how many tickets were going to be purchased. I could compute the probability of winning. You multiply those two numbers together and you got really, really close to 3. And so I just said, well, it's the number of winners. I didn't say this out loud. The number of winners is Poisson with parameter 3, but if I do, so I just gave them this command. Let's see, 1 to 7. Whoops, that's not what I wanted to do. I wanted to do this. If that's to spell plot correctly. Okay. And I got this plot, and I said, you know, my best guess is 3, but it's probably going to be between 1 and 5. Maybe I should have put in 0. But there's still a 5% chance that nobody's going to win. So that's what I said to them. And then the next day, 3 people won. And so the radio station thought I was brilliant, but all I did was type in DPOIS and plot it, and then said something to them over the telephone. Okay, so that's what I have to say today about confidence intervals. I'll get, no, they didn't share my winnings. They just are impressed that you can do quick computations on the binomial distribution. In fact, I got even filmed on that since I got asked. There was the probability of no one winning is exponentially distributed, and so they asked me what that was, and so actually I was filmed creating an exponential curve with parameter 3 to show them, given the number of tickets sold, what's the probability that no one won, and they were also happy with that. So there you have it. That's all I have to say today. If there's any, oh, there's another comment. If there's anything else, where's the film? I don't know. You have to go to the archives I can't remember what television station, but you have to go to the archives of that television station and find that out. I get asked about once every 2 years to say something about lotteries. Somehow they think the chair of statistics should answer that question, so they could say so. If I ask them if they would like me to explain it to them, and they always say no. So there you go. Okay, so we'll leave it at that. Any other questions before we sign off? Okay, so I'll see some of you at office hours soon, and the rest of you one way or another. I hope you're all doing well and staying healthy, and all your family and friends are doing well as well. Bye-bye now.